and joined the Department of Physics at the University of Hong Kong in 1993. He's now the chair professor of physics and has been working in the field of quantum transport of mesoscopic and nanoscale systems. Let's welcome Professor Wang, Jian Wang.
Thank you. Good afternoon. Today I'm going to talk about our recent progress in transport. Okay, so I'm going to talk about the transient current and second moment, we call short noise, and the full quantum statistics. I want to thank my collaborators. Some of them are in the audience. Okay, so this is the outline. So first of all, I want to give a brief introduction of what is the so-called full quantum statistics. Then I'm going to talk about a little bit about the so-called waiting time statistics. And then I'm going to talk about this so-called generating function, how to calculate, how to formulate the full quantum statistics. Then I'm going to give some numerical results for the some modeling for quantum dot. Then I'm going to talk about if you want to implement this one for the first principle calculation, then how do you do from this, the very beginning? You have to take the transient current, then the short noise, etc., etc. Then I'm going to conclude. The transport process actually is a intrinsically stochastic process. Therefore, that's why you need a current, average current, and also you need the short noise, and you need the second moment, third moment, etc. Supposing I have this device, then I want to measure. Here, suppose I can measure how many particles passing through. Then, of course, I can count how many particles per unit time. Then I got the average current. So here, suppose I got the detector here. Then I can detect. So then I can talk about at a particular time how many particles, how many electrons I can have. Then I can plot this histogram. Then after a certain time, I can do it again. Then I have another one. So what I'm interested in is this this distribution. For instance, what is at this 1 second, for instance, how many particles I have this distribution. So this is the quantity I'm interested in. Now, in order to calculate this quantity, of course, you can do the measurement. Then we actually do Fourier transform for that, which gives you so-called the generating function. So once you have this generating function, which depends on this parameter, this lambda, then of course it depends on the time. Then I can calculate all the transport properties. So this is so-called the full quantum statistics. For instance, you can calculate. So if you do once you have this generating function and you do the reverse Fourier transform, then you can get this probability. From that, you can calculate all sorts of the transport properties. For instance, the jth moment. If it's the first moment, that will be your average charge transfer. Okay. Then you take time derivative of that, you get the average current. You take the second moment, and you take the second derivative of that, you get the correlation. Okay. This is the correlation. So actually, you can get all of the quantities you're interested from this generating function. Okay. So this is people call the full quantum counting statistics. Now, the reason we were interested in the high order moment is because of this stochastic process is not Gaussian. If it's a Gaussian process, then you just need the average and its second moment. But intrinsically, is you need all the moments to characterize this process. Okay, for instance, here this is your the first moment. That will be the second moment. Now, another motivation to study this high-order moments is related to the entanglement. Okay. So, for instance, if I have a system here, then it can be divided into two parts, A and B, and suppose I got the pure state, which extended through all the A and B, then I'm only allowed to measure, to take the measurement in this part A. Then I want to know what is the information I got from this part B. So then, of course, because the wave function is delocalized in this region, therefore, of course, there's some interaction between A and B. And if you do the measurement in A, then, of course, you will have some entanglement information. So, for instance, here, I got this quantum point contact. If you control the gate voltage, of course, you can allow the charge to transfer from one side to the other one here. If you put gate voltage, if you open the channel, then of course the electron will propagate from one region to another one. Of course, you change the gate voltage and you can close this channel. Okay. Then, of course, they sort of, people call it the entangle. Okay. Then you can calculate you can study the so-called entanglement entropy. So this is the von Neumann definition of the entropy. Now this is of course very difficult to measure. How do you measure this density matrix, the entropy? Well, those people have relate the entanglement to the full content statistics. This Levitov, they prove that this quantity, the entanglement, the entropy, can be expanded in terms of all those high order cumulants. Now, by measuring or calculating those moments, then of course eventually you can get that. And this experiment actually has been done. So this is for a quantum dot here. So what you have, you've got a quantum dot over here. Then you operate that in the Coulomb blockade regime so that you can have electron come in one by one. And you apply a kind of a higher bias voltage so that the transport is in one direction. You don't want to, you receive once you detect the electron, it can come in from either side, from left or from right. So here you apply the voltage so that you can only have one direction transport. So you can easily detect how many electrons I get from left to right. Then here you put a quantum point contact, and which is very sensitive to if the electron is in the quantum dot or not. Therefore, this quantum point contact can serve as a detector, to detect how many particles you have, how many electrons you have. Then with all those information, then you can plot experimental data. So you can actually measure this. What is this? This is the fourth order, fifth order, high order movement up to the 15th order. So this has been done for quantum dot. That's in the global chemistry. Okay. Well, there's another interesting quantity. People usually talk about this full counting statistic in the long time limit. Okay. So, but of course, the short time behavior, this information has not been covered or has not been discussed. There's another quantity of interest, which is this is supposing I got a sequence of events. So during this time, I got 4 events here. Then what I want to know is I would like to know what is the duration, what's the distribution of the successive events. Okay. This has analogy. Once in mesoscopic physics, suppose you have a system called quantum dot, which we call chaotic. If you look at the spectrum and it's not regular. Then people are interested in how the entity levels distribute. People usually ask this question: what is the statistical level spacing? Now this has an analogy here. You see, those are the events in the time domain, and here entity level. So they have a very good analogy here. So this level spacing statistic is very much like this temporal correlation, or this is what we call the waiting time distribution. Okay. How long it waits before you detect a particle, and you ask, what is the probability I got another particle? So this time is called the waiting time distribution. So this is an important quantity we would like to study. Okay. Now, in order to study this quantity, waiting time statistics, it turns out that you have to find another quantity which is called the idle time probability, which is that during time t, I got a particle. I want to know what is the time, what is the probability that I got no particle, no detection of particle after time t. So this is called idle time. And of course, once we have this generating function, I will do the inverse Fourier transform. I got this probability. And if you set that equal 0, that's our idle time. And this problem has been studied, this waiting time distribution. And for the DC problem, if you start to detect a particle at time t0, after a certain time, you want to know what is the waiting time statistics. And this Bluetooth group has formulated a formula. So if you have the idle time, you calculate from this generating function, then you can calculate what is the waiting time statistics. So what we're interested in is what if it is in the transient regime? How do you calculate that? So it turns out that the formula is a bit different. This is how many particles during time from 0 to t, and this is, if you subtract by 1, this is the idle time. then you take the derivative of this equation, you got, another relationship. Anyway, so here, as long as you get the generating function, and you will know the information of all those high order cumulants. And from that, of course, you can get quantities such as this entropy, or you can think of some other quantities which can be related to the high order cumulants. And also here, we're interested in the waiting time distributions, then we calculate the idle time, which is also coming from this generating function. And we can, depending on which regime you're talking about, DC or transient regime, you can use this idle time to calculate what is the waiting time distribution. And also, you can show that if you want to measure this quantity, you can express this quantity in terms of this high order cumulant. Therefore, you can depend on how many cumulants you can measure, then you can approximate. Eventually, you can get this waiting time distribution, and if you have the information from the experimental results. Okay, so now I'm going to talk about this, how to calculate the generating function. You usually want to calculate the current, and want to calculate the short noise. This is what we usually do in the framework of the equilibrium, non-equilibrium Green's function. So what you first do is you define a current operator. Then you take a quantum average of that. Then you take, using this Landgraf theorem, you do this analytical continuation. Then eventually you get this Landau-Filter type of formula. Now, then of course this is the average current. If you want to get the short noise, what you do is you have to take the correlation of that. You got two kind of operators. Then you do this, linear continuation, which is very complicated. Then eventually you get another one. Now, of course, you naturally ask what is the third movement, okay? Higher order movements. Now, this one is not that well defined. The reason is, if you got three operators, the operators at different times they do not commute. Therefore, this is because you got two of those. You can do a symmetric form of that, and you get this short noise. Yes, you got three of those, and people prove that you got any symmetric form of this, that would not give you the correct one. Okay, so this is can be a problem. So, people use different approach for the quantum for the high order moments. So this is the original approach. So this full quantum statistics has been started a long time ago. It's back in 20 years ago. Levitov and Lesovik. So those are the pioneers. So what they do is they use this so-called the Gedanken scheme. So supposing you got the system, you got current driving through, then you imagine you got a spin detector attached to your system. For instance, attached to the left lead. Then what this spin does is, because you have a current passing through, then this current will generate a magnetic field. And this magnetic field, of course, because of magnetic field, this spin will process. And the processing rate is proportional to the magnetic field, which is also proportional to the current. Therefore, if you want to calculate what is the precession angle, that is proportional to the total charge. Okay. Therefore, if you can imagine that you measure how this electron spin with the time, then you can measure what is the amount of charge passing through. So this is the scheme. Therefore, what you do is you have the Hamiltonian of your system, then you also have a Hamiltonian of the spin, and they interact. Then you have the whole Hamiltonian, then you focus on this electron, this spin, then how this spin processed. Then from the angle of that, then you can calculate what is the charge passing through. Okay, so this is eventually, if you do this formulation, then you get this formula here, which will cause cost. Okay. Now, this one they claim is not invasive. It's non-invasive because it can be proved that it only changed the phase of the electron. It will not affect, because you have put some interaction of the spin with your system. Probably that will influence that kind of environment, that will influence the behavior of your system. But it only change the phase of the transmission coefficient. It does not change anything of the reflection coefficient. Okay, so this is what they call the non-invasive. Now, what we approach is based on the so-called two-time measurement, okay? Originated from chemists. Those people are in the chemistry department at San Diego. They're interested in the statistics, and they formulated a so-called two-time measurement. And this has been used by Professor Wang's group in University of Singapore, doing full counting statistical phonons. So for that system here, we are interested in two regimes. One is so-called the DC regime. In the remote infinity, the lead and the scattering region, they are all isolated. And right start from the minus infinity, you turn on the perturbation. You turn on the interaction gradually, adiabatically, until t equals 0, then do the measurement. Transient regime is that we separate all the systems. They are all separated, isolated, until at t equals 0. We turn on the interaction, we turn on the voltage, the bias voltage. Then we can do the measurement, we can calculate the transient current. So those are the this scheme. So what is this measurement? So you have to take two measurements. And this is the wave function, okay? This is a number operator, and this is the wave function of this number operator, and if you do the measurement, it will give you the number of particles over here. Then I can define a projection operator. So if you do a measurement, you actually project. You do a projection. Okay? So whatever wave function you have, you use this projection on this wave function, then you got that eigenstates. Then at the second time, which is after duration time t, I do another measurement, then I'm going to do another projection. Okay? So I'm going to start with a mixed state. Okay? For a particular pure state in here, then the first measurement at t equals 0, I do a projection. Okay, so this is my wave function. Then I can ask what is the probability, then I take the square of that. Then I can define a evolution operator from t prime to t, and here this is time ordering operator. So make sure that because they do not commute, so I put this one over there. So you start from this wave function here. You do a measurement, so you make a projection. Then at t equals to 0, then if system starts to evolve, and you have this time propagator. You evolve to here at time t, and do another measurement. This is the final state you have. Then, of course, you take the modulus squared, that's the probability we're asking for. So this is the probability here, which is this one. Okay, just plug this in there. Then eventually you got the formula like this. Okay, this P projection operator P squared is P. Then of course you're going to ask what is this distribution, and here has to be, if there's n is 5, then this difference has to be 5. Okay, so you have this third function here. Eventually, you can formulate like this. Okay. And for transient case, our starting point is that they are all isolated. So this is our starting states. Okay. Then you can do the calculation. You can use this finite passing rule and the non-Green's function, and eventually you can have this very neat formula here where I got this generating function, and which is this determinant, and this is the Green's function, usually the Green's function we have. Then I got this Green's function. I have this tilde. That is that because I got the left lead, which is my detector. Therefore, I have to modify my detector using this matrix here. This lambda is my matrix, which depends on this Pauli matrix 2 by 2. Lambda is my so-called counting field. Now you have this counting field, and once you have that, then you take the derivative, you get all sorts of moments. Okay. So this is very different from the previous one. You have to do this analytic continuation, but now here you can do anything. You just have this formula here, then that's done. Okay. Now, this G, this Green's function, and this self-entity, they are all in so-called Kelvin space. Okay. From minus infinity to 0, and go back to minus infinity, so this is a complex time loop. Okay. And this matrix has this form, except for this modified self-entity. Okay, so this retarded Green's function, if you like, and this is advanced, and this is another one which is related to the lesser Green's function, and you can easily check this one here. You take the derivative with respect to time, and you can easily get this curve. This usually is another formula. You take the logarithm of that, you take the second derivative, and you get this Short-Norris. Okay, so we use this one to calculate the numerically. Suppose I got one dot, and I want to know if they are originally isolated from leads, and if I turn on at t equal to 0, the interaction between leads and the quantum dot, and also I turn on a bias voltage. I want to know what is the transient current, what is the short noise, etc. Okay. So it's here, and also it depends on the temperature. So the different temperatures, I got this one, or oscillating, all that. So this is a very simple model here using this familiar form here. And also you can calculate using different composition here, because we know this is probability detecting n particles multiplied by n, that will give you a total the transfer charge. Then you take the derivative of that, you can get the current. Therefore, I can calculate this one as a function of this piece of n. And you can see that if I'm in the transient regime, then when this n equal to 1, you can either receive particle from left or from right. Okay, you only receive one of the particles because it's this voltage is not large enough. Okay, therefore you add them up, m equal to -1, which is the electron coming from the right, and this is the electron coming from left. Okay, 2 particles, 3 particles, etc. Then eventually this converts.
So where do I see? Usually I see quantization charge. I see steps as a function of voltage. If you change the voltage here, can you reproduce an experiment where I see essentially
yeah. So what I have,
charge steps in a dot?
Yeah, what I have is coming down here. I got one level there.
Yeah.
Then I got the originally no bias. Now I got the bias over there.
I understand.
Then this is.
But when you integrate up, you should see just 1 electron, 2 electrons, 3 electrons, and so forth. Do I see the Coulomb diamonds that I normally see?
No, I don't have this. Not in Coulomb regime.
No, but can I operate?
Yeah, sure. If you have included
your calculation in that.
Yes, you can do in the Coulomb blockade regime. Yes, you can do that. But we're not doing it.
I know you're not.
Yeah, sure. We can do that. Yes. By the way, this formalism is valid not for the counter regime, but Coulomb blockade regime, I think we can do that.
Under regime, yeah, but that's just a little bit.
And the reason for that is
it's a T over U. So
yes.
What is T over U? What's the hopping?
No, okay. It's not because of physics. It's because it's formalism. If you want to get this formalism, you need this kind of quadratic form. Otherwise you couldn't get this formula. So this only works for non-interacting electrons.
Okay, so it doesn't really work.
Well, if it is Coulomb blockade regime, I think I can make it work.
Yeah. There's if the quantum dot works, the Cooper pair box or something else.
No, that's sure. That's a research project. Yeah. Okay. So here, what I'm showing you is that this is the waiting time statistic coming from. First of all, you calculate the idle time, then you take the time derivative, and you can get this is the distribution here with different temperatures there, and also I show you here what is this probability. And also you can get what is the short time behavior exactly, and the long time behavior, which is some behavior is the and also we can use this formula to calculate. I just want to show you that we can approximate the waiting time statistic using this higher order moments. Okay, so here this black curve is supposed to be the exact value, and you can use the 4th order up to the 4th order, up to 6th order, then gradually it becomes more accurate. Okay, now this formalism can also be used to calculate to couple with density functional theory to investigate the first principle calculation if you want to study the molecular devices. So in the following, I'm going to talk about the transient current. Suppose you want to do this full quantity statistics, you have to calculate transient current, short noise, etc. Therefore, I'm going to talk about this one, how to implement that. Now, the basic question in this Anyway, so the basic question people ask is, if you turn on the bias voltage, what is the response time? And then, therefore, of course, you send a pulse there, then you want to know, how it responds. And this is an ideal problem for the NEGF formulas. And there has been a lot of work on this research area. The first theoretical result coming from the Wingren and co-workers, and they solved this problem exactly, but they used a so-called wideband limit, which is a not very good approximation if you want to do the first principle calculation. Basically, you assume that the lead has no feature, so that the interaction between the lead and the quantum dot is independent of the energy. There's another theoretical approach by Guanghua's group using the iterate the equation of motion, and basically you can calculate the transient current, or you can calculate time-dependent current. And also you can iterate the time-dependent Green's function coupled with density functional theory. So this is the formula that they proposed, and they did a calculation for transient current for the time-dependent model, and using this wideband limit. You can also solve the Schrödinger equation coupled with density functional theory. So this paper basically outlined the practical scheme. How do you calculate the transient current using this approach? And they also apply this method to the one-dimensional time-dependent model. There is also an exact solution going beyond this wideband limit, and basically it gives you the Green's function. With the Green's function, of course, you can calculate the current. Then eventually you can use this method to couple with density functional theory to calculate the transient current. Now, how do you implement? This is the big question, very difficult. The first implementation, I think, to calculate the transient current through this molecular junction is by Guanghua's group. The first draft, first paper, they used wideband limit, and later on they have a lot of refinement of their method. Of course, you can also iterate the non-uniform Green's function. You can also iterate the time-dependent Schrödinger equation, and to get this transient current. But those are difficult to implement because we have exact solution for the non-uniform Green's function, and if you really want to implement that into the molecular junctions, is computational demanding. The reason for that is in that solution you got the triple integral, and very often the convergence is a problem because you got a lot of quasi-bound state along the new axis. So that's the problem. And we actually made an approximation based on this exact solution, and we compare this we call ansatz with a soluble solution. There's an exact solution available for quantum dots, and we made a comparison, making sure that our model and our approximate scheme capture the essential physics. And basically, this approximation goes beyond the wideband limit. It's very fast, and it also agrees with this model here, exact soluble model, and it also recovers various limits. Another possibility is that you just iterate this equation. So in the following, I'm going to report our recent progress. The first one is what you get if you just iterate this equation. This is very difficult because if you calculate the current as function of time for n steps, then it scales like n to the 3 power. So we're able to bring that to n squared log n. Now, if you assume wideband limit, then of course it's much cheaper. So the equation we start with is we got this equation. This is how to iterate the Schrödinger equation, and you got this memory term, which is that's the most painful term, and those are the initial condition. And once you have this wave function, you can calculate the current. So if you count the number of equations, that's n to the 3 power. There's another method which you can do, which is usually when you do the transient current, you send plane waves, which is extended in real space. But if you do Fourier transform that's localized in k-space, which usually is much more efficient if you do in k-space. So basically, people propose that you can iterate Schrodinger equation in k-space, which is more efficient. And one of the disadvantages of that is it takes huge memory. So we have, okay, so this is method how to do it using either the Schrodinger equation or the non-equal function. So we have formulated a similar formula for the non-equal function. Here are the numerical results. So we use this Schrodinger equation approach, real space and k-space approach, and for the one-dimensional model, sort of agree. Then we move on to the 2 dimensions, also agree. So this is, make sure that this is reliable. Then we took a simple one-dimensional atomic chain, so use this as a first principle calculation, and the k-space, real space, we also agree, and k-space is much faster. Then if you just want to iterate this equation brute forcefully, then of course it's n to the 3 power. And of course you can use a trick also used by Wang, then you can reduce that power to n squared out n squared. Those are the details. Then eventually you can show that if you increment that into this kind of device, and the scaling is indeed the scaling one. Okay, so here is the transient current. If you get that, then you can find out that for this system, and I got a huge resonance, and this resonance peak here, I got 60% of that coming from this resonance. How much time ago? 5 minutes. Okay. So,
Is that resonance correspond to an internal excitation?
No, this is, I got the system here. I got this is below the Fermi level. I got 1 resonance.
But physically, I mean, when I see a resonance, then there must be some inelastic process.
No, it's not. It's like I got many states over there, and the one state is weakly coupled to my leads. So that's kind of it. If there's no coupling, then it's localized space.
Yeah, but there's a state there. So I mean, that of course you have that thing in femtoseconds, right? So there's some number of that corresponds to some energy of some millivolts, right? That's some fraction of the volt. So
Okay.
what is
No.
that energy? What is the interpretation of that? Physical interpretation of that energy?
Okay.
Well, I mean,
Now in my system, I do not have phonons. I do not. So.
So you have an electronic state there. Right?
Yeah. So
There's
that's
a molecule. There's a molecule in there, and it has some electronic levels, right?
Yeah. That's exactly
And
electron levels.
Is that and that frequency that you get must correspond to some homogeneously, or what is it?
It's below the. I think it's below the Fermi level. Is deep.
So what he has is that he's got a state below the Fermi level
There's a
because
state.
of his H omega, which brings this level into his into the transport.
I understand.
So that's what you're saying.
Yeah, so that
That's
must
exactly
correspond
what-
to some.
So these are
Energy.
electrical resonance. Yeah, it's
There is there must be some level in that molecule, because if there's not a molecule, if what feature, let me put the question differently. I mean, you have
Sure.
you put that molecule in there, but what is the crucial thing you put in from about that molecule must be some knowledge of the
Right. This corresponds to a
But
one
there
level.
must be an exciton, well, there might be an exciton in there, but there might be some.
We don't have that physics including our Hamiltonian, so we don't have exciton.
What is in the Hamiltonian for that molecule, and what's in that dot?
so he's got a lot of levels from the molecule.
But there is some level.
And one of the levels.
One of the levels
is-
happens to have that energy.
Right, one of the level happen to be close enough to the Fermi level.
Yeah.
Within H omega. So that's exactly what you said.
Yes, he's a spectroscopic in some kinds of So change, and then if you change the bias voltage, you see other levels. Right?
That's right.
So it's an inelastic tunnel spectrum.
Yes, through this H omega. That's right.
Like inelastic is like, what
we talk about AC.
Wilson Hodas.
Maybe
I'm sorry.
No, it's okay. I can talk here. No, yeah, I most of that. Yeah, so it's fine. So whenever we talk about AC transport, it's always going to be inelastic.
Inelastic. It's inelastic tolerance.
Yeah, sure.
So in principle, I could have just looked at the. If I knew this, if I knew the states of my molecule, then I could guess what the answer would be.
Yeah, right. But it depends on how the leads will couple to the, yeah. Okay, thank you. So I will stop.
Well, he doesn't talk
I don't think I'm like.
Maybe
I will spend 1 minute to talk about this. There's another method which is much faster, which we use this so-called the CAP method. Basically, this is so-called the this is called the complex absorbing potential. What you do is that the reason the calculation is so complicated because of the self-energy, because you have infinite system, then people usually want to replace this infinite need by a complex potential. Therefore, it will absorb all the incoming waves, and there's no reflection, there's no transmission. So this is basically people use this technique in chemistry. So we use this one here. Basically, it will speed up this calculation tremendously and becomes all the method. And the first thing you have to do is that once you put on this absorbing potential, you have to make sure that you produce the exact same transmission coefficient you had as before. Okay, so you have to make sure that. And then, of course, you can systematically increase the size of this absorbing potential, making sure that it will converge. Then this absorbing potential is very simple, just like it's energy independent. That's the key thing. Then you construct a Hamiltonian. You see here, Hamiltonian does not depend on the energy anymore. This is the if you use this complex of absorbing potential, this is your Green's function. Previously, this is your Green's function. Okay, this Green's function has a self-energy here, and this depends on a complicated form like this energy. Therefore, if you want to find a pole here, that's impossible. And this one here, this is a complex number. You see here, this is complex. But here it's very easy to find out the pole, and you can plug that into the exact solution over there. Triple integral, no problem. You can use the theorem of residue. You can calculate analytically. That's the reason you can get this done for your array. So eventually, then you can compare this result, this scheme with the quote unquote exact result we get before. Then you can use this formula to do a more realistic model and calculate. Okay, thank you.
Any more questions for Jian Wang regarding the code?
I guess just to put on your talk for this talk, I mean, you should really, if you connect this with the photon field, obviously when you start getting oscillations like that, it's going to emit light as well. So can you add photon field to the calculation to see what the optical emission properties would be? I mean, one thing is can you do the theory of the quantum dot laser, which is electrically driven.
Okay, quantum dot laser, I don't know, but if you want to couple that,
Just to start on the LED.
If you want to couple the system with a
photon
QED cavitar, no problem. But I'm not sure about the laser.
That's the nonlinear device, but principally you can couple to photon.
Yeah, you see, if you have an AC field, it's already coupled to
sure.
But that's the classical. So you have to quantize your
electromagnetic.
That's right. Then you can do QED. Then no problem. We can do that.
So you should be able to get a quantum dot LED. You should be able to do essentially the first principle.
I have a question. I heard that this year's Nobel Prize in Economics was given to a person working on a generalized method of moments. When they look at the first field, like, is your work somewhat related to what they do in economics on the university?
This is actually not my work. This is the original formula laid down by those people in San Diego, those groups. And I just took their formalism and applied. We have to apply to the electrons. So this is not original developed by us.
So this full counting statistics must be much harder than just calculating a query.
Sure. Yeah.
Because you are calculating all the moments. So now, if you use your full counting statistic to look at this transfer problem, can you reproduce this Chekhov's result?
Yes.
You do.
Yeah, no problem. We actually our result. First thing we have to do that. Yeah, exactly the same. No problem. Yeah. So what you do is instead of calculate all those moments, what you do is you just calculate this generating function as function of lambda as function of t. Then with that you can calculate everything.
Okay, let's move on then and thank Professor Jian Wang.